3, 2, 1. All right, everyone, it's July the 9th. All right, let's do this. Get this one done first. Crawler log folder. The LeetCode file system keeps a log each time some user performs a change folder operation. The operation is described below. Move the parent folder of move to the parent folder of the current folder. If you're already in the main folder, remain the same folder. Move to the child folder named X. Is guaranteed to always exist. You're given a list of string logs, where logs are as the operation performed by the user at the ith step. The file system starts in the main folder. Then the operations in logs are performed. Return the minimum number of operations needed to go back to the main folder after the change folder operations. So we initially here, so we go to D1, we go to D2, back to D1, go to D21, stay at D21. Okay, so use this change folder. We do this times and go back to the main folder. So basically we just need to append and see how many there is, right? Okay, so basically we'll use because it doesn't matter, right? Yeah, it doesn't matter. So maybe what we can do is just, do right shift and left shift. What do you think? Maybe we can say int folders start at 1, right? And then what we're gonna do is for string L of logs. Well, depends on where I am. Well, because I'm gonna shift left, I'm in the left shift. So we have 3 types, right? If it's equal to this, we stay. If this, we'll do a left shift, right shift, right? We'll do right shift. No. Yeah, yes. We'll do right shift, stay, and this will go. Okay, so if we equal to this or this, right? So if L dot equals, let's do this string backup, right? String stay. Right, so if equals to backup, we should do it this way. If it's a backup and folders, I'll probably do this. Folders and 1 is equal to 0. Right, folders and 1, so we can do a right shift. So in this case, folders right shift 1. Else if L dot equals stay, that we don't do anything. So it's not equal to stay. Okay, so if it's not equal to stay, so we say if it's backup and this, right? Then we right shift. If it's not equal to stay, that means it's gonna be going down. Then we say folders left shift 1, right? And then We'll do that, and looks like we don't even need this. Yeah, because we don't need this, don't need this. Okay, at the end, we just need to count how many zeros. We say while folders is larger than 1, interest equal to 0, folders right shift 1, and the rest plus plus, and we'll return rest. $15.98. Use. Oh, how many times? Oh, you cannot do it that way. 10 to the third. Lord. Yep, it's not possible. Yeah, forget about it. So we just, can we use a stack? Yeah, this is actually just a stack. Stack of integer. Okay, stack of boolean. Stack new stack. Okay, and then stack.add true. Okay, so we say stack.add backup.pop. If stack is not empty, right, and it's not empty, we'll pop. Otherwise, stack.add true. Then we can just turn stack.size -1. Use stack to store the levels. But do you even need this? I don't need this. I can just say int folders equal to 1, right? And then we just say folders is larger than 1. Then we can say folders minus minus. And this we can say folders plus plus. And we say folders -1. Use an integer to represent the depth, right, of the file tree. Let's see. Yep, I think looks good. Oopsie doozy. Stay. Back. Stay. Interesting. Huh? How is this wrong? Equals stay. It's not equal to stay. No, it's equals stay. So we skip, right? The next one is backup. And folders need to be larger than 1, but folders currently is 1, it's not just 1, so that's also fail. Oh, I see. Unfortunately, oh my god, yeah, you're right. That's okay. That is totally okay. So folders equals folders minus minus equal to folders larger than 1, like that. Okay, so let's try this. Yep. Maybe I can do this. I'm not sure. Is this casting work? No, I don't think you can cast. That's a good question though. Can we cast? Java cast int, no, cast boolean to int. Probably not. Yeah, probably not. So we cannot cast. It's fine. This will work. Yep, works. Yeah. Okay, let's do this. Lowest common ancestor. So we've done this before, but this time we are going to try basically using 236. Using reset this. Oh, we have a definition. Okay, anyway, so this is slightly different than what I had expected, but the general principle is the same. So we are going to use practice binary lifting to solve this problem, right? So basically we need a function. It's called def case ancestor, right? Which means given a node, just tree node, and k, will return its ancestor. So we return tree node. Right? So this is the function, which is to define the kth ancestor. But to do that, we need two array. We need a, oh, what do we need? We need the ancestor matrix, right? So ancestor can be a list of int. Right, we need an ancestor matrix. Oh, but this one is not really a matrix because this is never said everything is unique. No.val unique. That's fine. No.val unique. Oh, no.val is unique. No.val is unique. Huh. Hold on. Interesting idea. Turn tree node. Can I just use numbers? 3. Will this work? Yeah, it will work. Oh, okay. Okay, then no need this. Right, node can just be an int. This is ancestor, and we also need depth. It's a list of int. Okay. So this is define a kth ancestor, which we have ancestor, we have depth. Now we just need to break down k. Right, break down k, and I need index equal to 0. Index equal to 0. So we go from right to left. So every time it goes, and while it's out, I say I will go up. Right. So we say while k, if k and 1 is equal to 1, right? If k and 1 is equal to 1, then ancestor, so result is equal to node itself, right? So if it is, then result shall equal to ancestor result index ancestor, right? And then k will be right shift, k or right shift, index plus equal 1. Right, so we go back again, and then each time the rest will become ancestor. Right, ancestor will be index. We go up a level, we go up a level until we go to the end. So the last one, the rest will equal to ancestor, whatever previous. And your kth ancestor will be, is it res or res 0? We start from 0, right? So we say we do, oh, I forgot. Again, it's a node, right? So we say 7 is 111. So it's this, and then we do 2, and then we do 1, 2, 3, 4, and then we go here, right? So rest is here, and I do 0. So rest now is here, right? Next one is 1. So rest is here. The next one is the rest become here. I think I just return rest. Right, and then we just return rest. Okay, so that's that. So def build create ancestor matrix. Node is tree node, right? And we need depth. Depth is going to be in. You don't even use depth. What do you use depth for? To compute. Okay, so I need a depth here. ancestor. Doesn't return anything. Oh, we need parent as well. Node parent. Okay. So what do? We say we are the node, right? And then I can have left and right. So I'm at my node. So I say depth. How many nodes are we talking about? We don't know. Holy crap. We don't know the number of nodes. That's okay. Then your depth has to be... Ugh. We do not know. Yeah, I guess it's fine. I can just be a list. Yeah, no worry. Yeah, no worry, no worry. This is fine. So what we'll do is change the definition into a dictionary. So depth will be a dict, int, and int. This is gonna be a dict of int. So same here. So this is gonna be a dict of int list. Won't change much, right? Okay, so depth node.val go to depth. Alright. And then we shall say ancestor node.val right, because the first time I hit it, so dot append parent.val, right? And then we say for I in range from 1 to depths, right? And we start from 0, 1s, right? So we'll go with the 0 to the 1, right? So for each depth, we need to compute ancestor node.val append, right? Well, this what's the parent, and its parent should be ancestor node.val I minus 1, right? And it shall be ancestor of this I minus 1. So it's ancestor, and then we do I minus 1. Ay, Jimbo! Okay, so once we're done with the current, now what we're gonna do is we say self.create this node.left node depth plus 1 depth ancestor, and self.create this node.right node depth plus 1 depth ancestor. Oh, it might be none. Okay, so if node, ooh, I should check. If node is none, we just return. Okay. So now node is not none. Argument type none cannot be assigned to parameter node of type tree node. Oh, okay, so it should be optional. Tree node. Okay. Yeah, so you go left, you go right, so we're done with this. So just create ancestor matrix. So basically in here, what we're gonna do is we'll first create default dict list, right? And depth equal to depth just equal to a dict. Wait, how do you initialize a dictionary? I think this is a dictionary, right? So depth is this, and we say create self dot create. We have a root. Root parent is, holy crap. What is root parent? I always say a tree node of -1, right? Because its value is, holy moly. Yeah, but I guess it's fine. The root. Yeah, I think it's fine. Okay, so I don't like this one. Let's just do root. It's okay. Right, root's parent is root. And then we'll say depth. Depth is 0, and then depth and ancestor. Okay, so we create it, and then the lowest common ancestors. And this is when we need to do. We need to check P, and then we need to check Q, right? And if they are not the same level, we bring them to the same level. And after we bring them to the same level, we will find its, yeah. Hold a second. Doesn't come out anymore. I just said it and it came out. All right. So we create this first, and then we compare the two, and have like one if it's like depth 1, the other depth is 4. Actually, we can write it, right? If 1 is at, so this is 0, 1, 1, 2, 0, 1, 2, 3, 4. And then if we say this is P, this is Q, then we know that they have difference, so we need to find its 1, 2, 3, the third. Okay, so what we can say is PV is equal to P dot val, QV is equal to Q dot val, right? If depth PV is larger than depth QV, okay? If PV is larger than QV, then I want PV to be smaller. So if PV is larger than, so PV QV equal to QV PV. Right? So this is a dict of integer and a list of integer. Okay, so we swap them, so make sure PV is smaller than QV, because PV is higher up, right? Then we'll redo QV shall equal to ancestor original QV, and the depth shall be depth QV minus depth PV. Okay, so we get a new QV. Now we can do this one and a one level going down. Right, so we go to the top, then we go here, because they're on the same level. So we go ancestor, if it's, yeah, so what we can do is for level in range from the highest is depths. Oh, hold a second. Yes, so we will do that. Okay, so depths PV, actually from PV to 0, right? So if PV is, let's say, 3 depth down, so 0, 1, 2, 3, so 1, 2, 3, so we go 3 first, and then we say if they are equal, then we shall lower it down, right? So we say if ancestor PV level equal to ancestor QV level, right? If the two is the same, right? If the two is the same, then we shall say continue, right? Because we are going a little bit lower. Else, if they're not the same, okay, so probably we should just go direct to say if they're not the same, right? If they are not the same, then we shall move them up, right? PV move up, QV also move up. So we say PV shall equal to ancestor PV level, QV equal to ancestor QV level, right? So we move both up because their ancestors are not the same. So we move them up, and then we go. And eventually, the level will become 0. Right? A level will become 0. Then their ancestor is going to be, I think the ancestor is going to be 0. So we shall return tree node ancestor PV 0. Right? Because if the same, we just reduce. If it's still the same, reduce it all the way to 0. Or we do this and then we reduce all the way to 0. Okay, let's try this. Killing the mosquito using a giant cannon. Oh shoot, list out of range. Huh. Interesting. Ancestor append current vow. At current depth. And now we have I minus 1. If node is none, turn. Otherwise, so is it at the beginning? So we have root and root. And depth is 0. Okay? So depth of root is 0. And then so we don't do, so depth equal to 1. We'll go to the left. So I'm on the left, depth is 1. So depth of 5 is going to be 1. And ancestor 5 is going to be a list with an append. Append 3, right? The root is 3, so append 3. And then from 1 to 1. So still is nothing. Okay, so we probably need to... Okay, so I've got 1 call, so that's 3. And then I got a 5. Huh. And then we go to Well, would it still be able to print out? Okay, I just want to know. Can I print? Is it possible to print? Yes. So we go 3, there's nothing. Go to 5. Go to 6. So your 6. Depth 3 is 0, 5 is 1. And 3 point to 3. And a 5 point into 3. 5, 0 is 3. 3, 0 is, yeah, I guess it's fine. And next, or is this already have issue? So the depth is 2, right? So the depth is 2. Oh, wait, hold on. Shouldn't this be log? Yeah, I think it should be log. Yeah, we get a depth, but this is log. So it's not depth. It doesn't go to depth. It should go to as long as it's not a depth. So this I should turn it into log math.log2, right? Math.log2 depth, or I can say, okay, or maybe it'll be easier right here. We say I go to 1 while 1 left shift I is smaller or equal to depth. Then we do this, I plus equal 1, something like that. Let's see. Okay. Oh yeah, that's the same thing, because it's not really, we can't really use a depth. It shall be, oh, screw me. So we have a depth, but this is not, the level shall be, oh, I was trying to avoid, but I think we're going to the math.log2 of this. I'm not sure even it has this, so we have to int this thing. Alright? Int this thing. Oh, no. This is right. This is the level. We don't call this. We call kth ancestor. Oh my god. Yeah, this is wrong. So, AP shall be self.kth ancestor. Oh my god, this is so wrong. Alright, let's put it back here. Okay, so this is wrong. So it shall be ancestor of P shall equal to self.case ancestor. Node is P, K is level, and we have to pass ancestor. And ancestor of Q, self.case ancestor, Q level ancestor. And then this is going to be if AP is not equal to AQ, right? Then PV, QV shall equal to AP, AQ. Tree node. Huh? Argument type cannot be assigned to parameter node of type int. You tripping, man. What are you saying? Oh, PV, QV. There we go. Okay. Let's try this. So now we have the depth, so we do this. Yeah, this is also wrong. This is also wrong. So QV shall equal to self case ancestor QV. This is depth QV minus depth. This is the number and ancestor. Right, so QV we do case ancestor, so we get that, and then we do their case ancestor, and if the case ancestor is not the same, we do that, and then we do, so eventually level will be 0, so we'll do its 0's ancestor, right? Because we do its case ancestor, and then you reduce, and we do case ancestor again, and then we move there, and we do case ancestor, levels ancestor, and eventually we'll do 0 level, and the 0 level will be the same, right? The 0 level, that will be the same, and then we come out, then we basically just do what if they're the same originally? So the depth, so it'll be the same. Yeah, so what if QV and PV are already the same, right? And then we go from this, that way equal, and then because the level is 0, so I think I need to do a check. So if PV is equal to QV, then we just return tree node PV. Otherwise, we'll go through this. So now we're sure that they're not the same. I don't know, will they eventually just go to the same value? Yeah, if you see this, AP and AQ's ancestor eventually is a 0. And if they're not the same, no, they will be the same. Yeah. If these two are the same, and then when I come out, shouldn't that just be, so when they come out, it's the same, just do AP, right? Because at the end, it must be the same, because we will hit a 0, right? And then it's guaranteed that they will move to a certain point, and AP is not bound. Yeah, that's actually right. AP is not bound. Okay, let's try this one. If it doesn't work, then we will handle it tomorrow. Okay. Okay, so try it. Oh. Oh, because we have negative value. Holy crap. Okay, so it has to be a dictionary of dictionary. Alright, I'll do this tomorrow. It's good practice, but we'll do it tomorrow. Alright, I'll see.